Okay, let's start continuing the op-amp chapter. So just very quick review from the op-amp. So what we learned from the op-amp circuits is actually yesterday we could see what kind of topology we can use with the op-amp. So initially we started with the simplest topology, right? Which was like a unity gain um, structure that is useful for using this as a buffer because the input impedance is high, the output impedance is low, the voltage gain is almost 1, right? So that's why we call it a buffer. We checked, we realized that in this op-amp circuit, actually, we can check whether the feedback is positive or negative. So in order to do so, we need to try to force, let's say, the output voltage to increase. Then we go around the loop, see how this voltage change is actually the op-amp response to it. So if, for example, for this, if the output increases, then since this output directly connected to the negative input, basically this is increasing. And then since this is a negative port of the op-amp, it pushes the output to be going down. So we are seeing that if we try to increase this, then the op-amp is trying to return it back. That's why we say this is the negative feedback. And then we realize for the op-amps, once it is in a negative feedback mode, basically the op-amp tries to minimize the input voltage. The input voltage means the positive port and the negative port, basically that it tries to make it similar. So in a negative feedback, V in plus of the op-amp will be equal to V in minus of the op-amp. And then this is the way that we actually use this to solve the op-amp circuits. So we check that there is other type of configs that we can use this, like having one feedback resistor like this, R1, R2. Here was V in, here was V out. So this is a gain stage. It can provide a gain of R1 over R2, but it will be negative gain, so we say this is an inverting amplifier because of this negative sign. And this op-amp, the input impedance is R2, so it's not infinity. And then there was another type of gain stage that could be non-inverting. Right, the config was like this. V in was here, V out was here. Assalamu alaikum. Then AV was 1 plus R2 over R1. And then we also check that it is possible to actually change the R1 or R2 with different impedances in general. So we could basically make like integrator if we put the C here, or we can make it differentiator if we swap the C and R. right? And we check that there are some non-idealities with op-amp. The non-idealities was one of them was the offset voltage. We model it based on an unknown DC supply at one of the inputs. This is the way we model. It was showing that if the two of the input, let's say, are shorted or grounded, then we expect that the output should be zero. But in fact, in the real case, there is some minor difference between the negative port and the positive port, so that once you are making both of the inputs zero or shorted, then the output will not be zero. So in this case, basically, let's say the output will be that depends on the gain of the op amp times the offset voltage. So in order to compensate this offset, you need to somehow apply a reverse input voltage to compensate it. And then if you plot the characteristic of the op amp, basically the V out per V in, which means, so you expect that once the V in is zero, then the output should be zero, but it is not really zero. So this shift basically from the origin basically is the offset. Right? What else we consider? We check that the op amp may need some extra bias current at the input because the circuit basically internally is some sort of the transistors, right? This transistor sometimes need some base current. So internally they may need some bias currents, right? Which we are not seeing from the outside, but they are there. So we figure out that this drawing current from for the bias actually may make extra voltage change or extra offset somehow once you are trying to put your, let's say, your feedback. Then let's say for this one, the IB1 is actually is coming through the R2, which means it is generating some extra voltage on R2, right? And we need somehow compensate it. So one of the compensations was we try always keep the similar impedance from each negative or positive port. So if you see this, actually the impedances connected to the negative port is R2 almost in parallel with R1, just roughly, right? So to compensate the other side, basically we try to, in fact, have the same resistor connected to the ground instead of just directly make it short. What will happen is the current passing through this parallel R2 and R1 basically change this voltage, which we didn't expect. But on the other hand, we have the other port, which is pretty much similar, and it is also drawing some current. So if we connect the same, almost same impedance, we are trying to minimize the two voltage difference between the ports, right? So overall, we minimize this voltage difference because of this bias currents at the input of the op amp. So it will not generate extra voltage at the output, right? So these things were what we Uh, Yesterday. So today, I guess we will continue a little bit more to check the op-amp in terms of the speed. So yeah. So other than those limitations, we have extra limitation as well. So the one of the important limits are actually for the all electronic circuit is the speed limitation. So far we are talking about the op-amp gains, but the gain basically has a profile over the frequency. So at the beginning, we are assuming the op-amp is something like two input, V in plus, V in minus, right? And then it is like a voltage, dependent voltage source that makes the have a gain of AV like times V in plus minus V in minus, right? The ideal case actually does not show any Smith limit. Means that once you apply a voltage, like a sinusoidal voltage with any frequency, basically it can give you this much of AV gain, right? For every frequency, right? You are not seeing that this equation changes over the frequency, right? No matter if the frequency is very low or is very high, it has the gain, the same value. But in practice, it is not possible you to generate this very broadband high gain. In practice, every circuit has some limits that is actually the gain will start dropping. So the simplest model that we can make is assuming that the circuit has just a single pole at certain frequency. Means that before the pole frequency, you can tell that the gain is almost flat and almost the high value that you want, like A0, right? After reaching the pole, basically the pole means that it is like a first order circuit, right? After reaching the pole, the gain start dropping, right? So this is also the case for the op amps. And this limit for the pole actually is coming from the internal capacitances of the device. Because you remember, in order to have this first order uh, circuits, basically you need to have like some resistor and capacitor, right? Or some inductor and resistor, right? All of these cases can make some poles, right? But where these capacitors are internally, they are actually inside the device, right? So you had the, let's say you are using some BJT device as the gain stage, right? So can you see where these poles are? Where are those caps? So if you remember, for our small signal model, we are modeling like this, right? For the transistor, GMVBE, right? This is the initial model that we are using. So based on this, basically whatever you calculate in terms of the gain, it doesn't have any cap, so it is pretty broadband, right? It is not, it doesn't have any pole. Then, can you tell where these poles are coming? Do you have any idea? Do you have any idea? So if you remember, once we had the P and N junction. Do you remember? So the PN junction basically, if you remember, there was some junction capacitor. So how was this happening? Basically, some extra hole from this P region moving to the N region, and the electrons were moving to the P region, right? So they once they go there, then they will leave some depletion region here, right? And some electron will be left to here. The hole will be left to go to the right side, so they some negative ion left there, right? So this depletion region basically makes like something like the cap, which we call the junction capacitors, right? So now we were actually ignoring that kind of this junction capacitor, we call it like internal capacitance or a parasitic capacitance because we don't like it, so we call it the parasitics. Originally, we don't like to have it. We want to have very broadband gain, right? For all the frequencies, but they are there. So these junction caps, actually, the base emitter of the device is a junction, right? It's a diode. So basically, it has some, other than the R pi, basically, it has some parasitic capacitor, right? We just ignore it at the beginning. But later on, we will actually consider this. So on the other hand, we have this base collector capacitor, right? Means that there is a cap from the base to the collector. So what will happen if the frequency go to very high? These caps impedance becoming short, right? And once it becomes short, it means that you are basically connecting the base to the emitter to the collector. Everything becomes like a single node at a very high frequency. So you can easily see that the device is not there. Everywhere is just shorted to each other, right? So that's why the device cannot work as a good amplifier at a higher frequency. And you will see that the gain will drop after a certain frequency, right? But anyway, still you can use the op-amp, though it has the some cutoff frequency, let's say. And then if this one is the op-amp open loop frequency response, means that you don't have any feedback, basically. You get the highest gain. You get the highest gain. And it shows some frequency that the gain start dropping, right? But on the other hand, once you apply the feedback, basically, you are basically dropping the gain. But the frequency response, basically, at the high side is not changing that much. But overall, what you see basically is that the gain looks a little bit more broadband. In fact, uh, the bandwidth looks like expanded, but the gain is lower. So what you will see, in fact, is the gain is lower, but the effective bandwidth of the lower gain is like higher. And how much is higher? It actually depends on how much you are dropping the gain. So at the max, we define some parameter for the op-amp, which is saying that what would be the highest frequency that op-amp can work, basically once the gain reach to 1. So this frequency, we call it unity gain frequency. This is the highest frequency that the op-amp basically can at least work with a gain of 1. So Basically, this unity gain frequency says that how fast the op amp is. So this kind of speed of the op amp is will show on the other ways as well. So the name of that kind of limit of the speed is called the slow rate. So we have several cases for the op amp. Basically, once you apply a step function at the input. First, let's assume the step function that you are changing the input is the variation is not too big. Means the small step you are applying to the input. So as you saw earlier that the op amp is not fast, right? So the output ideally should be like a step with a high, maybe with some gain. But in fact, because the op amp has some speed limit, right? It is like there is some pole, right? There is some pole in the frequency response, right? This pole basically makes it like a first order circuit, right? The first order circuit, the response to the step basically is like exponential, right? So what you are seeing that the output is changing like exponentially and reaching to the final value. And then if you increase the input size of the input step, basically a little bit more. So what you expect is to basically have the higher step at the output, but since there is a pole, it kind of reaching to the final value with the exponential, right? Like this. But in fact, there is another effect. If you make the input step very big, then there is a region that op-amp actually even cannot follow it like the exponential. It will be most likely like a ramp going up. So, so maybe initially for the small signal it would be like this kind of thing, but you will see that for the bigger one, this slope will be limited to some certain value, right? So the difference is here. So for the small one, we are seeing that the slope at the for the small input is smaller. For the larger input, the slope is higher initially, right? But after increasing the input a little bit more, so you expect for the bigger input, it should have larger slope at the beginning and like exponentially settle, right? But after certain value, then you increase the input, the final value will be increased, but the slope is not increased. It's, it remains at certain level. If you even go higher, the slope is not changing initially. This is called the slow rate, means the maximum slope that the op amp can change the output, right? So this is another limit for the op amp. Is this clear? Just again, maybe describe it once more, maybe. So there are two cases. Just want to maybe better to. So first of all, now we know that the gain of the op amp is not just flat over the frequency. It has some pole, right? And we know if you have this, let's say, first order pole, then the output to the unit step is basically like an exponential with the time, right? So dv out. Exponential means once you apply some like step input, you expect the output reach to some value, right? Some final value. It start from 0, for example, right? And then it reached to the final value with some time constant, right? So if we increase the step amplitude at the input, so the final value should be scaled, right? Should go to higher value, for example. So what we see is that they always reach the final value at certain location, like for tau, right? It is coming out like this, right? So you expect this continue. So if you increase the input step size, then we expect that this shifts continue, right? Like the next level, let's say here, right? They are all reaching to the final value almost close to 4 tau. But at certain region, you are actually trying to go the next level for the step. For example, let's expand this a little bit more. So you expect the next step is reaching to this value because of the bigger input step. What you expect is that it should be something like this. But in fact, what you will see is that it cannot, the slope of the slope cannot be faster than this, basically. Goes like with this slope, not the higher slope, and then reach the final value. Then we realize that the op-amp has another limit that means that how much the output, with how much rate the output can change, basically. There is a limit. This one we call it the slow rate. Slow rate. So it cannot be larger than something value. And the way we report it is like something volt per second, right? It says how much volt per second is changing. Right? Yes. You just really apply a large input step and you can see this, measure this red curve and see how fast the output is growing up. It's like a constant slope. It keeps going constantly. That is the maximum. If you increase the step size furthermore, this slope won't change. It just, the next level would be like this again, starting with this slope and then, for example, going for the another level. Stop. So this is the maximum rate that the output can change basically for the op-amp. 0 means it cannot change at all, right? What do you mean? Very sharp. Ideally we want it to be very sharp, but in practice is not. Yes. So basically there are two limitings. One is because of this pole is limiting the sharpness of the output, because the pole basically says that the output would be similar to like the exponential. So the exponential always is like this, right? It needs some time to settle down. Cannot be too sharp. On top of this, there is another limit that it doesn't allow the rate of the output change even further. I mean, it cannot be larger than certain value. Because the exponential itself, it doesn't limit the slope. If you increase the input voltage, I mean, in the input step, still can be exponential, but the slope changes. Basically, this change the slope of the initial phase, right? Though it is taking time to settle down, but the slope may change yet. But at certain level, actually, the slope cannot even change. So this is another limiting factor. right? So two mechanism basically. So here is trying to show that how it should be if there was not that the slow rate problem. So it is showing that basically it should comes up like a exponential thing like this. I mean, if you just assume that the limit is the pole basically should be like this or this. They are coming up like with exponential. But in fact, in the real case, there is some limit. This slope limit actually changed the shape furthermore. So here is trying to describe what will happen once we have this kind of a slow rate limit when you are applying the some sinusoidal input. So in fact, it is saying that the highest basically change of a sinusoidal input, basically the slope of the input, basically. You can take a derivation from the sine and it comes up that it depends on the omega, right? This is just the derivation of the sinusoidal input or at the output, doesn't matter, right? Once the frequency goes higher, you have some larger slopes, right? Because the sinusoidal thing is faster, so there is sharper transitions if the frequency go high. This is trying to tell that. Depends on the omega. And if this transition is faster than the slow rate of the op amp, then it means the op amp cannot basically follow. And once it cannot follow, basically the output would be like this. So originally, it should be something like sinusoidal thing. But since this slope of the sinus is larger than the slow rate of the op amp, then the op amp, the maximum it can reach is this constant slope, right? So what you will see, in fact, would be something like this, right? Because the slope of the op amp cannot be as more than this value. So what you will see at the output is that the waveform is kind of distorted, basically. So we have another constraint for the op amps that is more clear. Basically, the op amp has some biasing uh, port supplies, and then we usually expect that the output of the op amp can reach at least to the minimum to the, let's say, the negative supply, or here is ground, and at the max can reach to the VDD, right, the maximum voltage that you have. But in practice, as you saw for the BJT, basically, there is always some limit. It cannot really reach to the very final or to the very minimum. There is some limit that the devices become like saturated or going out of the active region. So the really final value of this maximum swing is depending on how is the structure where the devices will be limited. So basically from this, so it is trying to see what kind of sinusoidal input we can have, let's say for this circuit. The maximum swing of the sinusoidal thing that we can have basically would be like this, right? The peak to peak value divided by 2 gives the amplitude, right? The amplitude of this sinusoidal is V max minus V mean divided by 2. And then there should be some DC level to make sure that the output is at the middle of the mean and max. So we are adding this part to here, right? And then it is also trying to say what is the maximum frequency that this signal can still work without reaching to the slow rate limit, basically. So the way it is actually computing this is not that difficult. So basically it tries to see how fast, the fastest way that voltage can go from the, let's say, 0 to Vmax for the op amp should vary this much, right? For a sinusoidal thing, it needs to vary from I mean, to this amplitude over this time, right? And then you can find the slow rate versus the omega of the sinusoidal thing. So if the frequency is higher than that value, then means the op amp cannot actually follow it very well. So the final, I guess this is the last one. Yep. Which we already knew a little bit more about it, is that the output impedance of the model, we were always assuming that the output impedance is 0 initially, but we know that everything that we make actually has some limited output impedance. It cannot be 0. So this output impedance, if you draw the model with the output impedance, then you will figure out that some of the equation needs to be modified, basically, right? It seems basically this R out is kind of in series with this R1 once we were calculating the gain. So it makes some error from the original gain that was just this. And also has more effects once you are actually driving some load resistance, right? Once you are driving the load, then this R out becomes more important, right? So here, this chapter is telling this much about the op amp at the beginning. So now we are a little bit more familiar with the op amp circuit, and this is what we are trying to make in the electronic circuit or analog circuits. And then we know what parameters are important now, right? And then we try to see how we can make these circuits. So we continue to the next chapter, uh, which is in the direction of actually going to make this kind of op-amp circuit. Yes, I already, I guess, put it in the group, WhatsApp group. So how can we... So this chapter, basically, we try to discuss about the cascode stage and current mirrors. So let's see what we are looking for before going through this. So do you remember what was the gain of a common emitter? Let's start from here, going back a little bit to the circuit. So do you remember what was the gain for the common emitter, the voltage gain from V in to V out? So we should put the small signal model basically, right? In fact, we avoid to put it, but we draw it away once more. Gm times VBE. There might be some R out for the device. And then we have the RC also, which for the small signal is just like grounded, right? We short circuit the VCCs. Then here is the V out, right? And then how is the gain? The gain would be RO in parallel to RC, basically times GM. There is a negative sign, V out over V in. So how can we increase the gain? Because we are looking for the high gain for the op-amps, right? This should be a building block for the op-amp. How we can increase the gain? So from this equation, how can we increase the gain? We can increase the RC, right? Any other thing we can do? We can increase the GM by changing the bias, right? There is some RO. RO also depends on the current, right? So the GM is what? GM is depending on the bias is IC over VT for the BJT. The RO is the V early over the IC. So it means that if you want to increase the GM, you increase the current. But on the other hand, the RO will be reduced, right? So from this part, the ultimate case basically means that the RC is going to infinity, right? And then what will remain is GM times RO again, right? But from here, what we are seeing that the gain actually is not that much changing if the IC changes, right? Basically, the maximum gain is VA over VT. This is for the BJT. This is for the BJT. So for the BJT, the maximum gain you can reach basically is this value for single stage. So at least we are seeing that we need to increase the RC to the maximum that we can, right? So how we can actually increase the RC? We want to increase the RC, but once we are trying to increase the RC, what will happen to this circuit? Can I put really infinity for the RC? Basically, the bias has the problem, right? If you increase this RC too big, then the voltage drop across the RC is too much. And then the collector voltage is, because the VCC is some constant fixed value, right? You put some 5 volt, for example, and you try to bias the device with certain current, like 1 milliamp, right? Then if you increase the RC, this collector voltage start dropping until the device go to the saturation, right? So it's not practical to increase the RC too much. So what if I try to bias the device like this way? I put a current source. What will happen? V in is here, V out is here. What is the problem? No, there is this current source. The current source has some impedance maybe. Ideally, the current source from the AC perspective is what? For the small signal? For the small signal is how? The voltage sources are short. MVBE, they are out of the device. So what should I do for this current source? It's open, right? So if we could put this current source basically here, it looks like we are putting like RC is infinity from the small signal perspective, right? But does it have any problem with the bias? Because for the RC, it has a bias problem, right? If you make it infinity, then this V, the collector voltage will drop, so that the device go to the saturation. It cannot work in active mode anymore. But is there any problem with this for the bias? So what is the voltage of the collector? Can you tell? Is this current source push the collector voltage to go down or not? It doesn't force it because the current source actually doesn't force the voltage to be something, right? It doesn't have any force on the voltage across it. But the resistor has it, right? Once you have some certain value of the current, then the voltage already known. But for the current source, basically, you don't have that much of limit. The voltage across the collector can be anything, but it still can provide the current, right? So this does not have the DC problem. At the same time, it has the highest impedance for the collector. And then if you could really put this current source basically here, you can reach the highest gain possible, right? So in this chapter, basically, we are trying to figure out how we make these current sources, and this cascode stage, we will see what is useful for, right? So we realized that the output impedance of the device, we try to increase it. And we are seeing how we can increase basically the output impedance of the device. So if you remember, one of the way was to adding some degeneration emitter resistor, basically, or some source impedance for the MOSFET, right? So if you remember the R out for this kind of device, when you look at the collector, basically, for the BJT was something like this, and for the MOSFET is almost similar somehow, like this, right? Can you see these two are similar? How this MOSFET and this BJT output impedance is similar? So in fact, the MOSFET, the R pi is going to be infinity. If you assume that the r pi is going to infinity, actually you come up with the same equation for the MOSFET, right? So in this case, then basically we can actually increase the R out of the device, right? We are increasing the R out because if we increase the R out, we know that somehow we can increase the gain, right? So what if we actually, instead of adding some RE over here, we just put another transistor? What would be the R out, right? It is similar to this, right? We just change this RE with another transistor, Q2. So the model for this transistor basically, so the small signal model, you need to just make this bias voltage grounded, right? And what we left is just the R out of the device, basically, right? This, you can just tell that the small signal is like this. The Q2 is just what, there's some output resistance will left over. And then you can again calculate the R out of this config, right? So this is the equation. So, but you can simplify it, right? This is the original equation. So how we can simplify it? We know that the R out of the device is considered as a big resistor. Remember, R out was that big resistor comparing to the R pi. So this can be simplified as just R out. And then the other side basically is just R pi, you can say, right? This can be like R pi. So what will remain basically is that actually this even can be more simplified, just R pi 1. What remains is that the R out can be R1 times R pi 1. Is it? So comparing to the just a common emitter, normal common emitter, the impedance of the device was only R out. But now you are seeing that there is a factor. It has the R out, but there is a factor of GM 1 times R pi. This value basically is larger than 1. Can you tell how? GM is IC over VT, and R pi is basically beta times 1 over GM. Maybe I write it the other way is better. We have the GM, and the R pi is 1 over GM times beta. So basically it's like beta times, right? So we can see if we have this kind of device at the bottom, then what we see at the output basically is like beta times of the R out, right? With this config, we call it the cascade, having two stacked devices on top of each other. So what we are seeing basically stacking up the two devices and looking at the collector of the top device, we are seeing like impedance is, which the impedance is beta times higher than the normal, right? So it can give some clue that this structure showing the higher impedance, so it might have a higher gain. Because we know that the higher gain means the higher impedance may be translate to a higher gain. So here is trying to say that, in fact, if we could have this ideal current source, so here we had this transistor here. The transistor is kind of like acting like a current source, basically at the bottom. If we could have the ideal case, then the maximum R out was this value, which we were simplifying, right? So what if we furthermore increase this calculation? Instead of putting the Q2, we add another RE to it. We can again calculate this R out, right? So from here, we can calculate the R out seen from the bottom side, which would be like this. And then one step more, you can go to find out the R out at the top collector by assuming that this R out is here. Right, but this does not that much helping to reach the higher value for the final out R out if you keep continuing this. Because as shown here, basically, you are trying to make the better current source basically at the bottom device, right? By adding this resistor, you are increasing the R out. So you make it better current source. But even if you put the ideal current source, the final value would be just limited to the beta, and RO1 doesn't change that much. That's why we may not keep continuing stacking up more devices. It doesn't help to increase the R out furthermore. And this is again same thing for the PNP device, right? The PNP device pretty much similar, just the direction of the currents is changing, right? So let's see. So here is just showing what kind of other type of connectivity is possible to make some cascades or stacking up the device. Basically, here it is trying to connect a NPN with PNP. But if you look at the R out for this, is it high or not? In fact, what you are seeing from the X is the emitter of the device, right? What is the impedance seen from the emitter of this Q2? Do you remember? You remember once you looked at the emitter, what was the impedance seen? You could transfer it from the base to emitter, right? The base is R pi, but from the emitter is, you remember, was 1 over beta times, right? Because the emitter current is higher, so the impedance is lower. So it would be 1 over GM, right? So seeing from the emitter is not big impedance. So if you connect the devices like this, then what we left at the emitter basically is just 1 over GM. We can actually ignore the RO2, right? The RO2 was from here. is too big. This is too small, this is too big, right? And then you can calculate the R out for this once the impedance at the emitter is 1 over GM2. So if you calculate it, basically, you will see that the with estimation, it will not be larger than 2RO1. But the other case we were trying to initially actually was like beta times of the. I mean, this is not a good connection for the cascode. It's trying to say because the R out is not that high. It is higher. It's like just 2RO1. But the other cascode that we were talking initially basically was like this, can reach up to beta times R out. So it's much higher. So for the MOSFET devices, we also have similar things, pretty much similar, right? So we can have the PMOS device. The small signal models are similar, right? And then, okay, yeah. So now we are seeing that we can increase the impedance by stacking up the devices as the cascode. So let's go back to the initial case again. So we can define for the device in any config. For any config, we can define some transconductance for the device or for that topology basically. So let's say you don't know what is this topology, but you can define some transconductance for it. The transconductance means you basically assume that the output is short. You are driving the input with some voltage and you want to see how much current is passing through the output. The definition of the transconductance basically, right? You have some black box. It can be anything inside here. It has some input, some output. So you short circuit the output. Basically, I'm talking about the small signal AC model. And then you will figure out how much current is passing through the short circuit. And this gives the GM of actually the block. And we usually write it with a G of the capital G. So let's say for the common source or common emitter, what would be this GM basically? I mean the capital GM. So you short circuit the output and then you apply some voltage, AC voltage at the input, right? What you will have is you can just put the small signal model for now. GM like VGS for the MOSFET, right? We apply a Vin. And then what we have done is actually we short circuit the output. And then we are trying to find this I out. So it might have some output impedance by itself. It has also some drain resistance, right? But once you make the output short, basically there is no current passing through this other extra resistors. So the equation will be more simple, right? Since I made the output short circuit, so basically the current is not going to pass through these resistors because the resistors, both sides are grounded, right? No current passing through the R out and no current is passing through the RD. Then all the current are just passing through this ground node that I put. Because you see that both side of the resistors are grounded. There is no voltage across the resistor. If there is no voltage, then there is no current on inside the resistor. So basically, this current source that we have, each current, whatever it generates current, it doesn't go through these resistors. So basically, the output current basically is the same current as this current source we have. Then for this block, basically the GM would be just the small GM of the device. Is this clear? If I apply some input voltage, it generates some current, which is GM times V in. And this current just go through the output. It doesn't go through the resistor. So the definition for the transconductance is this current, the ratio of this current to the V in, the capital GM. And in this case, the capital GM is actually the same as the GM. Yes, the output current to the input voltage. So if you know the GM of the device or the structure, right, then you can actually calculate the voltage gain by actually just multiplying the GM to the R out of that section. So this is the one way to calculate the gain of the device. So you are basically break it into two parts once you want to calculate the gain. First of all, you make a short circuit at the output. You try to find the GM. The GM tells that how much I out it will generate once you have the V in. And then if you want to calculate the V out over V in, basically, you can tell that the V out over V in is V out over I out, can like break it to I out over V in, right? We are looking for the gain, voltage gain, for example. So you can break it into two sections. One is this GM, we already calculated. And then this one is saying what? V out over I out. V out over I out is saying what? Is the output impedance, right? Basically, is the output impedance. This is the output impedance, right? R out. And I out over V in basically was the GM we were talking, right? So if you do it this way, actually, it's sometimes easier to calculate the gain. You break it into the two parts. First, you short circuit the output. You calculate let's say the capital GM, and then you will calculate the R out of the device, right? And then just multiply it. So again, from here, we can see for the higher gain, basically, we can try to increase this GM and we can try to increase the R out. So that's why we are trying to find the R out of this cascade structure, right? The cascade structure, basically, we trying to see what is the R out value because we are trying to increase the gain. And we were seeing that the R out of the cascade basically can be beta times higher than the normal, right? So again, it's going back to here. Let's say we have this common emitter. As we mentioned, we can bias it with some current source. So if we want to calculate the gain, we can actually first find the GM of this box. Let's say this is a box. So you short circuit the output of the box and try to find the I out. And if you do so, then the GM or the capital GM basically will be the small GM for this common emitter. And then you need to calculate the R out of the device, right? So you need to put as test source, right? This is the way. You ground the input, test source, and I test basically. And since this is a simple device, basically what will remain is just the RO. And this current source was already opened, right? At the collector, right? In fact, this DC current source is open, right? So again, you can calculate the gain with the same value we already know just by doing this way. So, so what if we try to calculate the gain for this kind of cascade section? How we calculate the gain? How we calculate the gain for this? This is the box, right? This is the box that we want to calculate the gain. Basically, can go to up. This is the box basically, right? So here we have the input, here we have the output. What is the procedure to do so? Right, we short the output. So let's draw the small signal model quickly. So basically here is ground, here is our input. What would be the base of this for the small signal? It will be just ground. The bias voltages are grounded, right? And then in our case, we actually ground the output, and then we want to find this I out. And here is the V in. So how can we find that value? I out to V in for this small signal model. Can you tell? Can you tell what will happen? How we can find the I out versus the V in? Basically, this is the small signal model, right? Of the what we want to calculate. So once you apply a V in here, so if we want to draw a little bit more, there was some R pi here, right? There is some current source here internally, right? GM times V in basically, right? I try to plot. There is some RO here, right? And from the emitter, what we are seeing is what? You remember what impedance we are seeing from the emitter? We consider, of course. Yes. So what we are, once we are looking at the emitter, what we are seeing, what impedance we are seeing, basically. Do you remember? Right? It is 1 over Gm, right? So in fact, from the bottom device, from the bottom device perspective, you have this V in, right? This R out of the device, R out 1, basically, right? There is one R out over here, right? R out 2. They are in parallel, right? Basically, doesn't do anything that much. But there is one over GM2, basically, right? Like this. So whatever current this device is generating is going to where? Is it going to the R out or going to 1 over GM? It's going to 1 over GM, right? Because this one is smaller, is much smaller than the others, right? So most of the current generated by this bottom device basically is going to the 1 over GM, right? Most probably is not going to go through the RO1 or RO2, right? So whatever this device generates, basically, the current basically just go to the 1 over GM, or even easier, basically, you can tell whatever this collector current is generated, basically, is going to be to the output. Because basically this collector current of the two devices are in series. Is there any path else that the current goes? There is, but most of the thing is going to, I mean, the collector current of this device basically is the emitter current of the other device, right? And then the emitter current of the device basically is pretty much similar to the collector of it. It's not exactly, right? IC over IE basically is like beta times 1 over beta, but this is pretty much around 1. So you can tell whatever this generates basically goes to the output. With this understanding, then the large GM would be what? Basically, which is I out divided by V in, is actually pretty much similar to the GM of the bottom device, right? So from the GM perspective, it hasn't changed. It's pretty much similar to the normal common emitter, right? The GM is pretty much similar to this, right? But the output impedance is much bigger, right? So the output impedance basically is this part. Can be much bigger, roughly beta times larger than the normal thing. Then this is saying that making a cascode actually amplifier boosts the gain maybe beta times comparing to the normal common emitter, right? The gain would be beta times higher. So if we could reach like the gain of 100 for the simple common emitter, beta itself is like 100. So just this single stage amplifier with a cascode basically can make a gain of 10,000, right? This is then a good tool for the op amp to make the high gain. So let's make the circuit a bit more practical. So we told that we need some like current source basically here to bias. But how we make these current sources? right? We need a current source to bias to reach that gain. How we can generate this by current source basically to bias? So this is the cascode part, but we want to put this current source over here, right? So what is the current source in practice? For the from the DC perspective, I mean. So for the DC, we have this batteries, right? The battery we have, but we don't have any practical current source. Let's say you have something like a battery that is a current source. Do you have? We don't have, right? Battery with a resistor. What kind of resistor? So you have this battery. What kind of resistor? Where? Is it series or parallel? So if you put a series, this is a way, right? Because we know that this has another Norton model. This is a Thevenin, so you can model it with the Norton, right? But what is the problem? If you want to make it the resistor is bad. We want really a current source. If you want to make it a very good current source, basically you need to increase this resistance to infinity, right? And if you increase this resistance to infinity, then it basically you are disconnecting the battery. So basically it's not working that one. Fine, right? So basically we are every the transistor actually when we are modeling, basically we are seeing that the output side is like a current source, right? The model for the transistor, basically what we put is there is a junction diode at the base emitter, but the outside is pretty much like a current source. It has the R out, but the R out is already large. So it's most likely to be a current source, the output side. So for this circuit to bias, basically we can use a transistor to bias it, right? So we use this Q3 to basically make it like a current source. So how it is like a current source? What is the direction of the current source? This is the PNP device. The PN, if it was NPN, basically the NPN is like this, right? We normally use it like this. The emitter is grounded. The base has some voltage, right? VB. And then the collector current is just this direction. So we cannot use this over here because the direction of the current is actually sinking inside to this device. But we want something that source the current to the bottom device, right? The NPN device actually sinks the current inside. But to bias this bottom block, we need some current source that actually source the current. So that's why we use the PNP, right? The PNP is similar to NPN, but only the direction of the currents are different. So in fact, the collector current for the PNP actually going to outside. And then you can use it as a current source to drive this node. So you bias this device again. The emitter is the highest voltage for the PNP. The base is biased, right? And it generates some current, and the direction of the current is in a good direction that we want, basically, right? So if you put it there, then this will be the small signal model, right? How? How is the small signal model of this Q3 basically? So this current direction for the DC is opposite, but for the small signal model, actually they are similar. The directions are also similar. So if you want to draw the small signal model for this, you need to short circuit here, right? Short circuit here because of their biasings. What we left actually is what we left actually is just let's try to plot it. Basically, it has some R pi. Emitter is here, grounded, right? It's connected to VCC but AC ground. This is the V bias is also grounded. And then this is the GMBBE, right? I draw it exactly similar to the NPN, as you see, right? The direction current, the direction of the current actually is to the emitter. And there is RO, and here is the collector. Here is the collector, right, of the PNP. Here is the VBE. So for this small signal, actually, since the VBE is 0, right? The base is 0, emitter is 0, right? So there is no current here, no voltage here. So this current source also not here, right? What we left is just this RO, right? So that's why you just model this current source with its R out, basically. And then now you can calculate the gain for this amplifier, right? So basically you have this kind of cascade structure here. The load is like the collector load is like RO3, right? So the GM of this section is same as before. If you want to calculate the gain, right? The GM is basically GM1. It's same as before. But how about the R out? The R out is the R out of this cascade device in parallel with this RO3, right? So the final R out is this value, right? Whatever we calculate for the cascade in parallel to RO3. So is it high or not high? How is it? Yeah. So the R out of the cascade basically is kind of like beta times of R out, right? Beta times of R out 2 basically. And this is in parallel with RO3. So what would be the final value basically? It's basically RO3, right? So the final gain is going back. We try to increase the gain, but the gain, the R out is not increasing, right? What was the reason? The gain has not increased this time. The GM is same, right? The GM is same as before. The R out for the cascade is same, but the R out of this current source comes into the equation, right? And the reason that the gain was not high, basically, because this RO is not high, right? So you try to increase the gain, you increase the output impedance of this black box or cascade itself, but you are now limited to the R out of this current source you put it. Is that clear? Oh.
a PNP transistor in parallel with Q2 and Q1.
So what kind of way?